When we have a function that can't be defined explicitly and we still want to look at the rate of change with these implicitly defined functions, we can. The only thing we have to remember, though, is that we're treating y as a function of x. And so for that reason, the derivative of y is not 1. The derivative of y is y prime, or sometimes we say dy dx. Now, where this can cause some confusion is when you're dealing with things like this example. If I have xy equals 3, for example, and I want to take the derivative or find dy dx, so I want to find dy dx here, then when I take the derivative of both sides with respect to x, I have to remember once again that y is a function of x and x is the variable. So when I take the derivative of xy, I actually have to use product rule. So product rule says the first, which is x, times the derivative of the second. The derivative of y is not 1. The derivative of y is dy dx. Plus the second, which is y, times the derivative of the first. Now, x is the variable, so the derivative of x is simply 1. So this is product rule of that expression, on that expression. And the derivative of 3 is 0. So now, to finish this example, if I want to solve for dy dx, it's just algebra from this point on. I subtract my y over, and lastly, I divide by x, and so here I get it. The derivative of y with respect to x is negative y over x. So if I'm looking for the tangent line at any given point, for example, all I have to do is plug in my y coordinate, multiply by negative 1, and divide by the x coordinate, and I have the rate of change of the curve at that moment. I'll show you another example, and I hope this makes sense. Okay, I want to find dy dx, where tangent of x over y equals x plus y. So here I need to take the derivative with respect to x of both sides of this equation, and here I'm treating this as a implicitly defined function. So what that means is I have to understand that y is a function, x is the variable, right? And so when you say the dx here, you're denoting that that's your variable. Okay, so to take the derivative of tangent of x over y, I'm going to have to use chain rule, actually, because I have tangent on the outside and x over y on the inside. So the derivative of that, the derivative of tangent, is secant squared x over y times the derivative of x over y. You're going to have to use quotient rule. So that says low times the derivative of the top, which is x, so the derivative of x is 1, minus the top times the derivative of the denominator, and here's where implicit differentiation comes in. That's not 1, that's dy dx, all over y squared. Okay, now on the other side of the equation, the derivative of x is just 1, and the derivative of y is dy dx. So now I just need to solve for dy dx, and it's not very clean at the moment, but hopefully we can clean it up some. So to do that, first I'm going to say secant x squared x over y, and I need to distribute that across this term. So here I have, first of all, let's write it like this. We have y over y squared, which I'll simplify in a little bit, minus secant x squared xy x dy dx equals 1 plus dy dx. Okay, so even though the y over y squared can simplify, at least I have all the dy dx's in a way that I can get them all on the same side. So I will subtract minus dy dx minus secant squared x over y times x dy dx equals 1 minus secant squared of x over y times, I'm going to just write this as y to the negative 1 power. Okay, so now what I can do on this side, I have a dy dx on both sides, in every term, so I can factor that out. And when I do, I'm left with a negative 1 minus secant squared x over y times x. And on the other side, it's not really much you can do. Maybe if you wanted to, you could write this as secant squared x over y. We'll just leave it as y to the negative 1 power for right now. And so finally, to get dy dx by itself, I just have to divide everything by this. And so here I have 1 minus secant squared x over y, y to the negative 1 power, over a negative 1 minus secant squared x over y times x. Okay, now to simplify this, there's not really a lot I can do, but I'm going to say dy dx equals, I'm going to take the negative out front from the denominator. So in the denominator it's going to give me a 1 minus secant, 1 plus secant squared x over y x. And in the numerator I have a 1 minus secant squared x over y, and y to the negative 1. I want to get rid of that y to the negative 1, so I'm going to multiply by y over y. So when I do that, in distributing the y across everything, okay, so that means in the top I have to distribute across here, and the denominator I have to distribute across here. But in doing so, I'm going to get rid of this y to the negative 1. So here I have y minus secant squared x over y times y to the 0, which is just 1. And let's make sure we understand that that negative's out in front of all of this. And the denominator have a y plus, I'm going to write this as xy secant squared x over y. Okay, and so there it is. That may be about as simple as I can get. So there it is, my dy dx. Now, I had to do some algebra in here to clean this up. I had to do this trick where I multiply by y over y. I had to make sure over here, I had to make sure to get all my dy dx's on the same side. So in order to do that, I had to distribute here first. I had to distribute the secant squared xy, and I also remembered that this simplified to y to the negative 1 power. So there was a lot of algebra going on in here. If there's some confusion, if you have a question, let me know. I'll be glad to help. Implicit differentiation, the implicit differentiation part is not as hard as the algebra a lot of times, but remember you have to get this dy dx by itself in order to actually have what the implicit derivative is. So if you have any questions, just let me know and I'll be glad to help. Thanks for watching.